Thank you very much for the introduction, Professor Marcus. It's my great pleasure to be here. First of all, I would like to thank the organizers and especially Professor Laurent Veron for his kind invitation. So I'm really delighted to give two lectures on singularities in this online mini course on singularities, block, and non-classical problems in nonlinear PDEs for youth. And the research I'm talking about is supported by the Australian Research Council. And briefly, I will start with some results that have already been mentioned by Professor Veron, but I think to make this presentation complete, I would like to remind them. And then I'd like to talk about main results in my paper with my former postdoc, Dr. Maria Frăcășanu, and the paper was published in 2021. And then along with them, I'll give foundational results and important ingredients that also can apply for other problems where you can include gradient factors, so more complicated problems that I'm currently I have in preparation, but these are very powerful, and you'll see that they can indeed be adapted to more general frameworks. So briefly, what is the singularity problem? As Professor Laurent Veron told us, if we take consider the very general framework of serine, quasi-linear elliptic equations of in divergence form of the form 1, in the right-hand side the function b, a scalar function, and consider it in a domain omega that contains the origin, and the solution in a suitable sense, which throughout the talk will be in the distribution sense, in the omega minus this point 0. What we want to know is, can the solution be extended in a natural way, that is in our case in the distribution sense, in the entire domain, and to satisfy it in the entire omega? If yes, then we say that the origin, this isolated singularity, is a removable singularity. Otherwise, and as a continuous also in this situation. Otherwise, I would say we want to know what is the behavior at 0 for this singular solution in the case of singular solutions. This topic has received a lot of attention in connection with the minimal surfaces, the Yamabe problem, mathematical physics. Here, just for completeness, I would like to just recall that Serine's pioneering papers in 1964-1965, published in Acta Mathematica, deal with a very general framework, where we have this beta 0 positive constant, and the other coefficients beta 1 to beta 5, beta 6 are actually in Lebesgue classes. And the epsilon that you see in the Lebesgue classes, you cannot delete it, really. So in other words, if you have a framework in which some of the one of these conditions is not satisfied, you cannot apply Serine's results. Really, you have to be careful about this. Then the result is a dichotomy. Either the solution, consider positive solutions, so starting from below, for example. In our case, we'll look about solutions that are non-negative. And the solution either can be extended as a continuous solution in the entire domain. Here, I'm taking particular domain, the unit ball, for example. So the solution in this case has removable singularity, or if not, is comparable with the fundamental solution of the P Laplacian, here mu or mu index P, as Professor Laurent denoted it. So the ratio between u and the fundamental solution of the P Laplacian is bounded from below and above by positive constants in a neighborhood of 0. And that corresponds to the weak singularity. So what we need to summarize from here to remain with is that the growth is done in order to apply this result, and we have only two possibilities: removable singularity, case 1, or the singularity is 0, it's weak, that is, you can compare it to the fundamental solution of the P Laplacian. Now, the Serine's papers have really generated a lot of research in order to see how situation changes if you consider nonlinear PDEs in which the growth of B dominates the growth of A. And this is a very challenging problem. I've been introduced to this theory of singularity theory to nonlinear second-order differential equations by looking at Professor Veron's book, and now he has also a more recent one in 2017. And so the challenge remains indeed to consider this case, the growth of B is bigger than that of A, and you see B potentially to include gradient factors, gradient terms, or singular potentials, and in short, this is really very difficult. there is no hope that you can make such a nice classification as Professor Servin's results. So what we need to do is to take special classes of equations and to try to understand what happens. And let me remind you briefly the case of semi-elliptic equations, because these are the pioneering papers. So if you take the simplest case, the domain being the unit ball, it's not really important. You can take an open domain, and just that essentially is to contain the origin, because you are looking for local behavior near zero. So you take a solution, let's say C1 on this unit ball from which you extract the origin, and you consider a solution in the sense of distributions, and which means that, that's important in the sense that equation 4 is satisfied for the test functions having compact support in C1 functions with compact support in the unit ball minus 0. And the question is, what happens with the solution near 0? And so if we did not in particular here find the fundamental solution of the harmonic equation, or mu index 2 in the previous talk of Professor Veron, then I just recall what removable singularity means, that solution can be extended as a continuous solution in the entire domain, entire ball here, and you take the test function then with compact support in the unit ball. And we have three results according to the range of Q. So Q is expressing the right-hand side. U to the Q is the power of U to the Q. So now if Q is less than or equal to 1, so Q is always, we take it positive. If Q is less than or equal to 1, then you have the Servin's framework. So we can apply the result I mentioned, the first one, in which we have two situations, removable singularity, or solution is comparable to the fundamental solution of the Laplacian. The second case, when Q is greater than or equal to n over n minus 2, which was done by Bresis and Veron in 1980, is that if n is greater than or equal to 3 and Q is above or equal to n over n minus 2, then there is a removable singularity for all non-negative solutions. And by the way, here, since we are in the case Q greater than 1, you have strong maximum principle. Q is greater than 1, you have strong maximum principle. So any non-negative solution is either 0 or is strictly positive. So you can read positive solutions instead of non-negative. The last case that is remaining, treated by Veron in his pioneering paper in nonlinear analysis in 1981, when Q is between 1 and n over n minus 2. So n over n minus 2 is here the critical power. So then we have three possibilities. Either 0 is in singularity, as we had it before, or U is comparable with the fundamental solution of the Laplacian. But moreover, we can say that actually the limit of the ratio exists, is finite and positive number. And the third possibility is that of a strong singularity, where U blows up faster than the fundamental solution of the Laplacian, and more precisely blows up like modulus x to the power minus 2 of Q minus 1 times a positive constant gamma index NQ, which is given here. Then how do we get the last, how do we get this trichotomy, the third case? Is simply you are comparing, you look at the ratio between U and the fundamental solution of the Laplacian, and you have three cases. Either U divided by phi has limit 0 at the origin. In this case corresponds to the removable singularity. The second case, limit superior U on phi is positive and finite. Then you can prove that the limit exists and coincides with this limit superior, or limit superior of the ratio U on phi is infinity, and that due to harmonic inequality means that the whole ratio U on phi diverges to infinity, and then you can improve and say that the third behavior happens. Okay, but now let's see very briefly how you get this critical coefficient. In this case, it is very instructive even for other cases to look for particular solutions. In the most natural form, when you have such power form in your power terms in your equation, is to look for a power form solution. So you call that gamma modulus x to minus alpha positive, and you need gamma positive as well. So you plug in this form in the two terms of the equation, the ones in blue and the one in red, you will see that you get that the power, the alpha has to be exactly 2 over Q minus 1, and from the red terms, the powers of R, and the gamma has to satisfy alpha q equal alpha plus 2, which give us the gamma to the q minus 1, the one in blue, gives us the value of the gamma. Now, in order for gamma to be positive, it's well defined and positive between 1 and n over n minus 2. So that's one way in which this can divide the point. Let's now go to the quadratic division. So now we are taking, with p between 1 less than equal to n, right to the q. We are looking positive again in the puncture ball, puncture net. So now again we have to distinguish three cases. The position of q with respect to p minus 1, what does 1 now becomes p minus 1, because the growth of the A in the left-hand side is p minus 1. So if q is comparable with the left-hand side, dominated by the growth of A, here p minus 1, if q is less than or equal to p minus 1, we can apply Serin's result. So we have that dichotomy. If, however, q is greater than p minus 1, then there is a critical exponent, which is, in this case, because we are dealing with p Laplacian, is n times p minus 1 over n minus p. Indeed, if you take p equal to, the critical exponent becomes n over n minus 2. So we have then the supercritical case, when q is above q star or equal to it, corresponding to p less than n, strictly less than n. Then we have that the origin is a removable singularity for every positive solution. And this was done by Vasquez and Veron, Manuscripta Mathematica 8081, and generalizing the case p equal to done by Brisis and Veron. Okay, then Friedman-Veron considered the remaining case in 1986, when q is between p minus 1 and the critical exponent, strictly less than the critical exponent, and generalizing the case that we said earlier, the three possibilities, we have respectively removable singularity, the first case, the second case is corresponding to weak singularity, and the third case, strong singularity. Again, you can reiterate the by hand what kind of strong singularity you have, and recover quickly the condition that q has to be less than q star and greater than p minus 1 in order to have strong singularities. Perfect. So the next thing is, how about taking more general nonlinearities? What about in the right-hand side, we take something that depends on x times function of u. This was the concern that this was the topic I became interested in, and in two papers, first in 2010 with Yihong Du, and later with my former PhD student Chang, we have generalized the results of Friedman-Veron and Vasquez-Veron, two nonlinear equations, elliptic equations, but more general form. In the left-hand side, we included a weight in the divergence operator, which we call A in red. And in the right-hand side, we said, well, what if you have a function of x and times function of u, and not necessarily power functions? So then, we will need structural assumptions, which will allow us to obtain something like a fundamental solution, because here is very important that what we are interested is to see, is it the p Laplacian, the solution of the p-harmonic equation, does it play a role here? No. If you include A, and A is general, like more general than is not constant, then you have to work with the operator in the left-hand side and look for find some kind of fundamental solution, replacement of fundamental solution here for the operator. So the condition on A are quite general in the framework of regular variation theory. But here, let's not use these words. So we take a C1 function. It's a power function times this L index A. It's a slowly varying function, meaning of the form that t, the derivative of this function divided by the function, goes to 0 at 0. And there is an integral condition there in order to allow us to create our fundamental solution. So we also need that condition satisfied always if you take the case that A equal 1. So that one is to obtain a fundamental solution. Then the natural condition A2, B is a positive function, continues on the closure of the domain except 0, H is positive, vanishes at 0, and you have a monotonicity, as a boundedness, H of t over t to p minus 1 is bounded for small t. And the condition A3 that tells you how to generalize H and B, how far they go from power functions, and can go very far in the sense that you multiply H of t behaves at infinity as power t to the q times L index H. This L index H are slowly varying functions. So think about the property that LA has, but at infinity. The limit TLH derivative over L index H goes to 0 at infinity. So that you can say that is normalized slowly varying function. And similarly for the right-hand side, for B, but at 0, because you want modulus S goes to 0. And the L index B is a slowly varying function. So think about logarithms, iterates of logarithms, powers of logarithms. All of this work very, very well. So then there is a condition there between Q, P, var theta, and sigma, which allows us to be in a generalization of the result that I showed earlier. So finally, we are able, with this, under these conditions, to obtain a fundamental solution for our rho operator that generalizes the solution, fundamental solution for the Laplacian. And this is in the form 9. So this is a constant, a normalizing constant, and that integral from R to R1, observe that phi is 0 on the boundary when R is 1. And this replaces what was the fundamental solution for the Laplacian when A is 1. It coincides when they equal 1. And then the critical exponent becomes now n plus sigma times p minus 1 over n plus this var theta minus p if p is less than n plus var theta, and q star is infinity if p is n plus var theta. So we have a removability result. The interesting question for us was, what is actually the condition? Should we actually think Q less than Q star, Q greater than Q star, and so on? So no, we have to be a bit careful here, because we have functions that can be very far from a power function because of those slowly varying functions. So what you need to look, actually, you have to check an integrability condition of b of x times h of phi. So in the right-hand side, replace u by phi, the fundamental solution of the operator, and check whether this product b of x h of phi is or not in L1 on a small ball centered at 0. And we have two cases. If it's not in L1 on the ball of radius 1 and 2, then this forces Q to be supercritical with this Q star above, and P has to be less than n plus theta. And in this case, this is the generalization of Vasquez-Verron's result, because in this case, every positive solution can be extended as a positive continuous solution in the entire domain ball. So that is the removable singularity case. But notice that now the condition is not written in terms of Q greater than or equal to Q star, but rather B of X H of U is not in L1. That was what we are looking to understand, the role of the right-hand side. So you see the right-hand side, the fundamental solution of the operator, in the left-hand side, whether it's in L1 or not. That is the way to get the critical condition. And finally, I mean, we would like to know what happens if B of X H of phi is in L1 on the ball of radius 1 and 2, centered at 0. So in this case, we are generalizing the trichotomy result Freeman-Veron. So we have either removable singularity in the first case, or we have the weak singularities in the second case, and the strong singularity the third case, where notice that now the strong singularity is not anymore in a simple form, because our functions in the right-hand side are more complicated. So the functions LH and LB have to appear in this relation 10. So the good thing is we can do it. And the corresponding existence results that show that this classification results are in fact sharp are done in this theorem 7, saying that according to, if we put a boundary condition, Dirichlet boundary condition on the unit ball, and then you impose at the origin all the behaviors that you expect from the classification, that is limit u on phi to be gamma, and gamma to be greater than or equal to 0, exactly in the range for which the classification is given, we will have solutions. So basically, we are saying that the classification is optimal. And then one quick word here, that such problems are of interest. This, including this weight A, is not an artificial problem, because if you take a weighted Laplacian equations such in the form of 12, and you take it this time on an exterior domain, with p greater than or equal to n and q greater than p minus 1. When you would like to know what happens at infinity with the solutions, if you apply a modified Kelvin transform, u of x vx tilde with x tilde over modulus x tilde square, then the behavior at infinity for the problem 12 reduces to the behavior near zero of the positive solutions of the weighted P Laplacian equation with the weight modulus x to the power 2 times p minus n, and with the b modulus x to a minus 2n and h of u to the q. So therefore, our results become relevant. They can be applied to understand the behavior at infinity for problems on exterior domains. So the weight plays an important role, even if you are considering P Laplacian equations on exterior domains. The third part that I will focus my attention on for the rest of the talk is the following: nonlinear elliptic equations with Hardy potentials. So this is another direction in which I became interested to see how the classification, what is the behavior of any positive solution when we include this singular potential, Hardy potential, in the left-hand side. So we have, for the simple case, well, simple in quotation marks, you take Laplacian of u as the operator, then you add the inverse square potential, and then in the right-hand side, you just take a product of the power of modulus of x and u to the q. And and we would like to take any lambda real, any theta real, and allow any q greater than 1. The reason for which we are would like to classify the behavior of solutions, but also at infinity, that is on exterior domains, and also to classify and prove existence of solutions to understand completely the structure of all positive solutions when omega is the entire space Rn. So in Rn minus 0, in other words, the solutions are in Rn minus 0. So these are quite intricate questions, and took quite a bit of time and many works to really complete it. So it has been completed in 2021 for this particular equation. The case Q between 0 and 1 was solved. The classification is completely done for the non-negative solutions, and is due to Bidoveron and Grillo. In 1999, and for this reason, from now on, I will assume Q is greater than 1. And now two good things really happen when you take Q greater than 1. One of them is have the strong maximum principle. So any non-negative solution in a bounded domain that does not contain 0 will either will be identically 0 or will be strictly positive. And then you can extend it, and you can do it, in fact, also on Rn minus 0. So another thing is that we have a comparison principle, and these are extremely important tools because, as you will see, in order to complete the open questions that remained for this question problem 13, a method, very powerful method, proved to be using local construction of local sub-solutions, super solutions, and those work because you have the comparison principle. So a bit of the background. So we have the papers of Gertsch and Veron in 1991, the paper from which I learned a lot. And then in 2014, I succeeded to completely classify the singularities, isolate the singularities near 0, not only for the power nonlinearities that you see in the right-hand side, but more general, similar to what I showed earlier for the P Laplacian, that is function more general than power functions in the framework of regular variation theory. But there is a condition there that lambda is less than or equal than this Hardy constant, then minus 2 square 4, and theta greater than minus 2. The remaining case, lambda greater than this Hardy constant, but still with the condition theta greater than minus 2, was solved in 2017 by Wei and Du. And finally, in 2021, with Ferkashanu, I succeeded to completely solve this problem in Rn and close all the open gaps, what was left undone. Now, of course, the inspiring models are the power case for Laplacian u equal u to the q in Rn minus 0. We know by the pioneering paper of Brezis and Veron in 1881 that there are no positive solutions, global, when omega is Rn. In Rn minus 0, there are no positive solutions when q is greater than or equal to n over n minus 2. When Q is, however, between 1 and n over n minus 2, then we also know the existence and profile near 0 of all positive solutions, C1Rn minus 0 solutions from the paper of Freeman. So then in 1986, so then what we wanted is to see how this complete understanding for such equations, how does it look like when you are taking a Hardy potential and weighted nonlinearities. And now I'm going to, so in order to make this presentation understandable and kind of distinguish the key players in this classification, I'm going to focus on the global classification. And you'll see how the global classification draws from the classification that is local, near 0, but uses the fact that also essentially that omega is Rn in order to see that globally many solutions that that would have been only local actually don't exist in Rn when omega is Rn. So we are luckier because many of the solutions die out when omega is Rn. So let me see the notation. I will denote lambda h n minus 2 squared on 4. These are best constant in the Hardy inequality. And there are two things that really are very important. So the first thing that one would need to try is to, can I find a solution in a particular form, or a particular solution of our problem, radially symmetric. And by hand, you can see that if I look for a power form solution of form 16, constant modulus x to minus some power capital theta. What is capital theta and what is that constant? And when that constant is positive, what we've done earlier. So we redo these calculations and we can see that the capital theta that will give us a particular solution U0 is that exactly theta plus 2 divided by Q minus 1. That's capital theta. But the next thing is we need a condition that the coefficient, this constant in front of modulus x minus capital theta to be positive, to exist, to be well defined. And for that one, we are led to define in this function f index lambda, quadratic polynomial in 14. We define it for every tiner, this quadratic function, and it plays a very important role, not only that it allows us to say when U0 is well defined. So U0 is well defined precisely when plugging in capital theta, this exponent, capital theta, you plug it in f lambda, and if the value is strictly positive, which I'll denote L, then bingo, we have a positive radial solution. But on the other hand, it also helps for another very important purpose. You see, the Hardy potential is helping the Laplacian, whereas the right-hand side is competing with the left-hand side. So what happens when you add the Hardy potential? That is not included in Serin's framework. Even if you take Q between 0 and 1 and theta, the right theta, you cannot apply Serin's result directly. So it's not possible because of this Hardy potential. So then the Hardy potential plays an important role. It becomes together allies with the Laplacian and forms this operator L lambda, and the solution, when the solutions exist for the operator L lambda equals 0, those solutions play a critical role in the classification. They will be in competition with the solution U0 that comes from the interaction of the left-hand side and right-hand side. So this is extremely important because that's the way we understand the classification. We have to compare the solutions of the operator, Hardy operator, let's say the left-hand side operator, with the solution U0, when it exists, of course. So then we can see that modulus x2 minus alpha solves L lambda, the operator in left-hand side equals 0, if and only if alpha is the root of f lambda, f index lambda. That is an important observation, and that happens, this equation has roots if and only if lambda is less than or equal to lambda h. And those roots are defined by p plus minus here in relation 15. And so immediately we get two important points. In fact, three functions that will play a critical role in the classification. They are the first three lines in this table. So whenever lambda is less than or equal to the critical, the Hardy constant, then we have in blue and in red, the two solutions of the operator. These are the ones that with which we'll compare our solution. whether the solution is dominated by phi lambda plus or not, or if it's dominated by phi lambda plus, is it going to be dominated by phi lambda minus? These are the questions that we need to ask. And finally, to compare the solution with U0. The profile U0 is extremely important when L is positive. And so, as we can see, now we want to understand the structure of solutions when omega is Rn for all positive solutions. And there are three situations that can appear globally when omega is Rn. And we have first a very nice result, which is the following. Whenever the f lambda, the quadratic function f lambda, does not have any roots, when f lambda of t is strictly positive for all t in R, this corresponds to lambda being greater than lambda h and theta in R. So we have no, the phi lambda plus, phi lambda minus cannot be defined. In this case, globally, there is only the solution U0. And that's it, because we already know that in that case, if f lambda is positive for every t, f lambda of capital theta, this little l is positive, you can define U0. And it turns out that that's the only solution. Global, I mean. The third, let's look at the third case because it's very nice. The third case is very nice because whenever you observe that little l is less than or equal to 0, and this corresponds to lambda less than or equal to lambda h, and little theta between theta minus and theta plus, which theta minus and theta plus are these numbers. Now you could write equivalently, if you want easier to keep in mind, is simply saying this condition, the last condition in n from non-existence. You can also say it when capital theta is between p minus and p plus. That is equivalent to little theta between theta minus and theta plus. These are equivalent. So in this case, when little l is less than or equal to 0, it's easiest to say. Then you have no solutions, no positive solutions. Of course, I'm always talking about positive solutions. No positive solutions in Rn minus 0. And finally, the multiplicity result, which is more involved because now this corresponds to what is left. What is left is that little l is positive, but you have the roots. You have the roots for you have the phi lambda minus phi lambda plus. That is, you have lambda less than or equal to the Hardy constant, and theta is less than theta minus, or theta is greater than theta plus. So I'll call this M1 and M2 because there will be multiplicity. We have multiplicity result here. Okay, so I'm very happy to have recently been contacted and heard from Professor Bidoveron that she succeeded to generalize and extend this classification for the P-Laplacian equations with absorption terms and Hardy potential. So this is a great achievement because this is not an easy problem. So this very, very interesting, is a different method. It's very, very nice to know that it's possible to classify globally for taking a Hardy potential corresponding, of course, associated to the P-Laplacian, and take P-Laplacian. So very, very nice. So coming back here in this table, besides the three asymptotic profiles that play an important role there, I added two more. Just this reference point disappear only locally because they correspond to the case little l less than or equal to 0. So the one that you see, the last at the bottom in black, those don't appear globally. Okay. So now, as before, just to mention that my solution is always assumed to be positive, C1 on omega minus 0, and in the sense of distributions. And the word subsolution will mean the changing equalities equals 0 in 17 by less than or equal to 0, and super solution you put greater than or equal to 0. So are understood in the sense of distribution. And the results are the following. So in case U was when f lambda is always positive, that means lambda is greater than lambda h and any theta in R, then the only solution is the solution U0, the one that we found by hand. And the crux of the proof, I mean, because it's easy to state but not easy to prove, the crux of the proof is to show what happens near 0 in case U. We also did it simultaneously in the case M1. So in case U and in case M1, we proved that every solution, every positive solution near 0 behaves like U0. So there's only one behavior locally near 0 if you are in case U or in case M1. And then what tools are, so let's assume for the moment that theorem 10 is proved and see what can we do further. So there are two tools already mentioned. The first one was already mentioned by Professor Veron, the transformation T sigma, which sends a solution into a solution for the same equation. So the sigma of u is a positive parameter. T sigma of u is a sigma to capital theta u of sigma x for every x in Rn minus 0. And you see that u0, our solution, particular solution u0, is invariant, left invariant by T sigma. And the advantage of this sigma will help us when we look at global solutions, even though they appear in one case as being infinitely many. In fact, it's just you just need one solution and then you apply the T sigma to that one. So it's very useful for classification, for characterization of solutions, to keep in mind this transformation. The comparison principle simply works. Here I gave one possible reference. We have to be a bit careful with the usual comparison principle because lambda can have the wrong sign for the standard classification, for the standard comparison principle. If lambda is positive, it's not the right monotonicity, but it does work in our case because our function g of u is u to the q, and g of t over t is increasing for t positive. So when I mean comparison principle, I mean that if we have a sub-solution denoted here by u in the sense of distributions on a domain that does not contain zero, the closure of the domain does not contain zero, since we have the zero is a singularity for our potential and so on. So we have a sub-solution u, a super solution v in the sense of distributions on v to omega, and the sub-solution is dominated by the super solution near the boundary of the domain, then the inequality extends in the entire domain v to omega. And the conditions for our problem, it applies for our case. So that is the one that I will be referring, and it plays an important tool. And another one is the Kelvin transform. Because in order to understand the behavior at infinity, you really can simply work only near zero, but allowing any theta in R, not restricting theta to less than -2 or greater than -2, allowing any theta. And then the Kelvin transform, if you understand everything near zero for any theta, you can use the Kelvin transform to obtain the behavior of any positive solution at infinity. And the Kelvin transform is the usual one in relation 19. And the way it changes when you apply the Kelvin transform, we have to be careful, because the equation has the same form for the u star, for the Kelvin transform of u. However, the power, the modulus, the theta, the power of the modulus x is not theta anymore, is a theta that is here denoted with a hat, which is changed, is n-2 times q minus n+2 plus theta. So that means that when you change the behavior at infinity, to get it at infinity from the one at zero, you have to change the cases. So I will just mention this paragraph. The important point is to see also how it changes the theta, capital theta hat, and is n-2 minus capital theta, and L hat remains L, which is a good thing. So the constant in front of u0, L.1 on q minus 1 remains the same. So now what we all these words here, really what I would like to emphasize is this paragraph, that if you are in case u, in other words, when f lambda is positive for every t in R, then the behavior at infinity can be obtained from the behavior at zero. Case u remains u, does not change. But when you are in case M1 near zero, that becomes case M2 at infinity. So you have to be careful to switch it correctly. And case M2 near zero becomes case M1 for the Kelvin transform solution. So that is the observation here. So then you're applying Kelvin transform, and the classification that we observe near zero now means that in case u and case M2, the behavior at infinity is unique, and u behaves like u0. So u0, the good thing remains the same. It's very nice. So that's very nice because now we can prove the uniqueness result immediately. I wrote too many words there, but it's really 2 lines. So how do we do that? We only need to observe that suppose that we proved that at infinity, any solution in case U, we know that behaves like U0, but also behaves like U0, near zero, in case U. So then we are in a good position to apply the comparison principle. Why? How do we do it? This is standard. You fix epsilon between 0 and 1 arbitrary, and you look at 1 minus epsilon U0. And because Q is greater than 1, you have super linear in the right-hand side, 1 minus epsilon U0 is going to be a sub-solution. And on the other hand, 1 plus epsilon U0 is going to be a super solution for your problem. But then you know that U behaves like U0 near 0 and also like U0 at infinity. So it means that you have inequality 23 if you are close to 0 on some interval 0 r epsilon with r epsilon small, or if you are with modulus x very large, larger than some r epsilon. Perfect, because now you can apply the comparison principle to extend inequality for every x in Rn minus 0. And then you take epsilon go to 0, and you prove that U has to coincide with U0. It's a very clean proof, and only you need to classify basically near 0, and that's it, because then you use Kelvin transform, get it at infinity, and comparison principle. So it's very, very nice proof, but the hard work indeed is to prove, the hard work goes into proving theorem 10. So the theorem 10 is the hard point. So that is a very good strategy. I mentioned this because you can use it, in fact, also if you deal with other more general problems with singular potential, even for P Laplacian, but for P Laplacian, you have to use the modified Kelvin transform, not this one, the one I mentioned earlier. So the Kelvin transform or the modified Kelvin transform are extremely useful tools that can help you to transfer the behavior from 0 to infinity and reduce your work. Yeah, so that is what I wanted to emphasize. The next thing is the non-existence. Again, a very short proof, provided you understand the behavior near 0. Very, very short proof. Slightly shorter than what is in the article. I changed here and there, made it a bit more. After some experience now, I can refine some things. So suppose by contradiction that we have a positive solution in case n. So case n means that little l is less than or equal to 0, which means this lambda is less than lambda h, and theta is between theta minus and theta plus, or just say little l is less than or equal to 0, this number here is less than or equal to 0. Then we can prove, and that also Professor Veron mentioned this, it can be proved that modulus x to capital theta u of x converges to 0 at 0. Okay, you can prove this. And once you prove that, apply Kelvin transform to say, well, this is also true at infinity. You just use Kelvin transform and you are done. But then what do we do next? It's very important this little l is less than or equal to 0. Why so important? Because if you fix epsilon arbitrary positive, this v index epsilon in orange, epsilon modulus x to minus capital theta. Now you take any epsilon positive, and v epsilon is going to be a super solution for your problem. And it dominates U both near 0 and at infinity because of 24 and because of 25. And so it means now that U is a solution, the epsilon is a super solution dominating U both at 0 and at infinity. You apply the comparison principle and you extend it in Rn for every x in Rn minus 0. And then you just have to take epsilon go to 0, fix x different from 0, take epsilon go to 0, and you get that U has to be the identically 0 solution. So a very, very short proof, which shows an important lesson. When you deal with this kind of problems of isolated singularities, and when I introduce the problem to my students, many of them say, why don't we do first the existence of solutions? And I tell them, for these problems, you first need to understand what kind of problem, what kind of behavior do you expect before you prove existence. Because it may happen that you may try to prove existence either when there are no solutions, you can find by some method some solution, not knowing which one are you finding, because in many cases you have more than one behavior, and then you don't know which solutions you are obtaining. So that's why first you have to classify, and then you prove existence, which simplifies terribly the problem if you know what kind of behaviors you get. So that was that's why I'm insisting on the classification rather than existence. Okay, so then the last result that remains in cases M1 and M2, that is a bit more complicated because we need to understand the behavior near zero. So let me say only in the case M2, because case M1, if we understand M2 completely for any theta, then we understand completely case M1 by using Kelvin transform. So case M2, if you remember the trichotomy that this corresponds, case M2 corresponds to what was in the results of Friedman-Verron. Okay, that is that case when Q is it was between 1 and n over n minus 2. That is what we are what corresponds here, but we are in the case that omega is Rn, and of course more complicated. So we would expect a trichotomy. We would expect that U divided by the phi lambda plus has a limit that is positive and finite. And that is true for every gamma positive constant. We can find exactly a solution that turns out to be radially symmetric that behaves like, has the property in 27. And we already know that that there is, we already know the behavior that is at infinity. We already know that in case M2 at infinity, you behave like zero. So we only need to understand near zero. And very important here that gamma equals 0 cannot happen. So in this limit in 27 cannot be zero. Cannot be zero in our, when the solution is in Rn minus 0. Those can't exist. So then the only other solution that can exist is U0. Okay, because case M2 means that U0 is well defined. Little L is positive, implies little L is positive. So then we have all the solutions. We have the solution U index 0, the one we found by hand. And if we denote this unique solution U index gamma, you take U index gamma for any gamma strictly positive. And here was the observation that you can relate U gamma, in fact, is not for N for U1. U gamma is nothing else than T sigma or T gamma applied to the transformation T sigma applied to U1, okay, with the corresponding sigma. So in fact, it's just one solution U1 and you apply the transformation to it. For any sigma, and then you take also U, and that's the so simplification. And for case M1, I don't insist because you just apply Kelvin's transform. And if you are curious to see an example where you can actually see an explicit form, you can take this case M2 theta equal of this form and lambda, of course, less than lambda h. And then you can find by hand, you can check that the solutions other than the U0 are of this form written here, which I want to read out. So it's very nice that it confirms indeed, and we can do by hand, we can check by hand that this is a solution. So it's an explicit form, but I don't know for other cases. This is for a particular case. Good. And now what are the tools? So we have a priori estimates already mentioned. Global here, in fact, the constant C0 is very nice. It's only depending on the parameters. So you take a ball centered at 0, the radius to R0, included with this boundary in omega. And then for every Q greater than 1 and lambda and theta in R, there's no restriction on lambda and theta. You can find a constant C0 depending only on the parameters, such that any subsolution satisfies the a priori estimate. Notice that with no coincidence here that we have exactly modulus x2 minus capital theta, except that we have the constant C0 here that is depending only on the parameters and applies for any lambda theta in R and any Q greater than 1. And I must say that it's extremely important that Q is greater than 1. Because we need that. We need for the comparison principle, this globe and the estimate. This is also applicable if the domain is Rn minus 0. If omega is Rn, then of course this will give you the estimate for any x different from 0. The inequality extends for any x in Rn minus 0. The sketch of the proof already mentioned, you basically what you need to do is to fix x0 with the what you want, modulus x0 less than or equal to R0. Look on this ball at this fixed x0 with the radius half of the modulus x0 on 2, and construct a super solution, which is here denoted by P, notice what happens. You look at the right-hand side, replace x by x0. So that's a constant. And the only function that you multiply by is a function that blows up on the boundary of the ball, because zeta becomes, this function zeta becomes 0 on the boundary of the ball, and you have to raise to a negative power. So this P is a super solution for our equation in this domain, in this ball, and blows up on the boundary of the domain, and so dominates any solution you take. You apply the comparison principle, and then you take x equal x0. And beautiful, because then zeta is 1, and P reduces to exactly C0 modulus x0 to minus capital theta. It's very nice proof with this construction of the function P, and Professor Veron also gave more details about this technique. Okay, so now the a priori estimates are extremely important. What you can do with them, lots of things. So maybe I'll just say what you can do with them, and then what you can do is a regularity result. So whenever you have estimates for your solutions, immediately, I mean, but you expect to get gradient estimates if the problem is nice, and you can in this case, and the gradient estimates are here in 40, so you get this in all these estimates that are written up. I put them in a bulk here, but all of them are extremely important. So all the constants that you see, d0, d1, d2, and d3, are depending only on the parameters in the problem. There is no other dependence. And so you take any positive solution, and with the respective, see this ball to be with the closure including omega, and then you have the gradient estimates for modulus x less than r0, and then you have the spherical Harnack inequality, again was mentioned, and then you can get this estimate 42 that is very, very useful, because it allows you to tailor the gradient estimates when you have any other upper bounds for u. And then finally, this last one, 43, which again is nice to put u here instead of particular upper bounds. And all these estimates are very important for many reasons. One of them, you can use them to prove existence of solutions by working on annuli and shrinking the inner annuli radius, shrinking to 0. So you can use these regularity results for the solutions to pass to the limit. And other very important application, the spherical Harnack inequality allows you to rule out oscillations near the origin, as already mentioned before, and to control to obtain the solutions that are comparable with the fundamental solutions. So let's say that you obtain that u divided by phi lambda plus limit superior of this ratio u divided by phi lambda plus is positive and finite. How do you know that the limit exists? Well, it relies entirely on this regularity result critically, and by a blow-up technique that was used by Firman and Veron, and I put some slides there, what you can do. So, for example, one very important application is this kind of. So you suppose you have phi, some function phi, which has a very important condition here, this limit r theta plus 2 phi q minus 1 is 0, and some limit here, again, that it's very important condition, and phi lambda of eta is less than or equal to 0. So the idea is that if you have the limit superior u over some phi that is important to you, one of the fundamental solutions of the operator, and is finite and positive, then you can prove that actually the limit exists. That is one of the important applications. I wrote this in more general. It's not like in the paper. This is more general, and in order not to repeat the argument, you can actually do it very general with general phi. So you won't see that written like this in the paper, but basically particular cases are included in this more general one. So the trick is very nice method. So you take the ratio, you do this scaling here, you fix r, and you do the scaling along u of r xi over phi of r. So r is fixed small, and you create this function v of xi, and you are using the fact that the various upper bounds that you have to get a priori bounds for V index R, for the gradient of V index R, and then you'll take a blow up the argument, and just to see that you, I don't have time to perhaps give all the details here, but it's you can adapt the Friedman variance technique with this more general framework to get a nice control of the limit of U. Okay, so what was something really new in the paper with Maria Ferkashan that I want to explain in a few minutes is how do we actually prove theorem 10? So that was very nice, and well, I'd like to say a few words about it. How do you get this theorem 10? How do you get the behavior near 0? That you behave like U0. The hardest part is not the limit superior U over U0 is less than or equal to 1. That's not the hardest part. It has been done earlier. I've done it in other papers. Is the lower bound. It's always the lower bound that is hard to prove in this kind of defined asymptotic. So the idea, yes, so what I would say, if whenever L is positive, that is whenever your solution U0 can be defined, you observe no restriction on lambda and theta. Whenever little L is positive, then you have the improved a priori bound. You have the sharp upper bound in the sense that limit superior U on capital U0 is less than or equal to 1. You see, in the a priori bounds, the limit superior here would have been something bigger. So now we are doing the sharp constant. How do we do that? It's a perturbation technique, and which also works very well if you have also information near 0 for like this in the form 33. So now if you take a super solution and it dominates modulus x to minus theta plus eta for any eta, it dominates it, then you can also obtain the optimal lower inequality. So it can be done in parallel by a perturbation technique. So how is it? I'm explaining quickly for the super solution, because you can do similarly for sub-solution. So what you do is you fix a sub-solution. You take a constancy which is strictly greater than the optimal constant, arbitrary, in the end will be arbitrarily close to this L over 1 Q minus 1 for the super solution. And then you construct a family of super solutions, P eta plus, which dominate near 0 and on the boundary of a small sphere, the boundary of the ball center, some small r0, it dominates U. And this extra property here, that when you take eta is the parameter that will go to 0, this limit times modulus x to capital theta is C. And you construct that, and this is simplified compared to the paper, so you can do it. You have to be a bit careful here. U is a parameter that you need to allow it arbitrary. Alpha is small, suitably small. You fix it. Nu is arbitrary, and then you prove that you can take eta sufficiently small between 0 and some constant eta index C, and this P with plus minus are supersolution respectively subsolution. And then it's very nice because you can apply the comparison principle to say that U of x is dominated by the super solution, respectively dominates the subsolution in the puncture ball of radius r0. Then you take eta go to 0. When eta goes to 0, and then you take you multiply by modulus x to capital theta and take modulus x to 0 and use the last property. And so you get the limit superior modulus x of U of x less or equal than C. But C was arbitrarily greater than L over 1 Q minus 1. That's the optimal one. So you now take C to converge to L1 over Q minus 1, and you are done. Of course, the hardest part is to prove what was the assumption that was made here, was that for every eta positive, we have that U dominates modulus x minus eta plus minus theta plus eta. And in other words, if you can prove that the limit inferior modulus x capital theta U is positive, then then 33 is true. Is this one here in lemma 18. This is the construction. You have to go away from the origin at the distance delta. And the reason is that W delta becomes 0 when modulus X is delta. And this ensures that the subsolution is dominated by every solution, because every solution will not be 0, will be positive inside omega. So you have the control. So you have to really go at the distance delta, make W delta to be 0 on the sphere of radius delta, and then that is the hard part, to find this form. Once you find it, the proof is by comparison principle. So I think this is important results that can be generalized. The sub-solution, I'm pushing this method now with other collaborators to work for more general nonlinearities, including gradient factors, singular potentials with gradient factors, right-hand side, which has complicated gradient factors. It really works. It's hard sometimes to find those sub-solutions and super solutions, but it's worthy because it works very generally in a very general case. And the asymptotic behavior near 0 in 10 seconds, it has been done completely for theta greater than minus.
Professor Cirstea,
yes.
Please, you have maybe 1-2 minutes till the break.
Okay. Yes, just this, and I finished. So this chapter 7 in my paper in Memoirs gives the complete behavior near 0 in this framework. And the critical change is this one. You work with radially symmetric solutions, and you apply this change for radially symmetric solutions. It reduces to a result of Taliaferro, and you can get the classification for radial solutions. And then the other two dimensions, radially symmetric, the Harnack inequality and the gradient estimates, everything else, it allows you to extend the classification from the radial solutions to any solution. And if you really want to see get a taste of what you can do with the results in that paper, here you can take much more general nonlinearities, and the situation locally becomes quite complicated. So I'm only listing it to scare you a little bit or to whet your appetite. So it's quite complicated locally. And that is my last slide. Thank you very much for your attention.
Thank you very much. Really, very, very interesting talk. Some small discussion maybe. My question, some small question. Professor Cirstea, whether you analyze some removability condition for point singularities, whether you know some results about removability of some more complicated sets, singularity sets, which have some another fractal dimension and so on, because such activity also exists. What you know about this?
Yes, I think there are. Haven't really looked to extend those results. There are, but yes, there are, because this singularity problem has been studied in other context, more general context, and yes, I think there are. Already Professor Veron mentioned the sum with the capacity, of course, by Serene, but it doesn't come to my mind right now a reference, other reference.
Yeah, I would like to say that NEE with Professor Konьков published last year some paper about the removability of such a singular sets for even for higher order equation, like Pila-Plashin. But if you would like, I have to send to you such a reprint of such a paper.
Yes, I'll be very interested. Thank you very much. Yes.
Because it can be developed in many other directions.
Yes.
So the subject was concerned my question. But I would like to say to you today, maybe you have to do some comparison which you know in context of this paper. Yes.
Thank you. Thank you very much. Yes, I will be interested. Thank you.
Yet question, dear colleague, what you wish to ask our lecturer? What is very interesting talk, and maybe you have such a question. Please, who would like to ask?
Let me ask a question.
Please, Professor Moravnik.
Professor Cirstea, thank you very much for your very interesting lecture. Could you get back to equation 13 for a while?
Yes. Yes, that's equation 13.
I mean, open slide with the equation. Open your slide with equation 13.
Sorry.
Please
So that's
get back to your slide where equation 13 is introduced.
Equation. So the equation is number 13.
Yes, equation
the one
13.
that.
Yes, exactly. I see.
That's the one. Yeah.
I see that Q is positive. Moreover, it is greater than 1. Then what is the reason to specify the positivity of solution in definition 8? Maybe it is enough to specify that it is non-negative, not exactly positive.
That's correct. That's correct. That's correct. Because of the strong maximum principle, it is enough to say non-negative. That's correct. The strong maximum principle holds because Q is strictly greater than 1, so you can say non-negative, and that either is identically 0 or is strictly positive. That's correct, which is why I mentioned the strong maximum principle. That's correct. For Q greater than 1, you can say U greater than or equal to 0, and if you say U different from 0, then that's equivalent to U positive.
Thank you. And one more question. Announcing gradient-dependent terms.
Yes.
Did you mean anything else, anything apart from P Laplacian?
So what I meant, the gradient terms will be here in the right-hand side. So it will be modulus x theta I to the q modulus gradient u to the m.
Yes.
And that's hard with m greater than 0. It's really very complicated. And with some other term, also drift term in the left-hand side. So it really complicates the situation when you include the gradient factor. Yeah,
yes, because
I've done it in a more particular case. Yeah.
Can you expect it in your next lecture tomorrow?
Really so. Yes, now we will do some break and it's a very interesting discussion. Maybe tomorrow we'll continue. I get that it will be very interesting to hear this continuation. Yes. Thank you very much. In general, thank you very much. So now we have some small break for 4 minutes. 4 minutes break now we have. The next lecture is 11:15.